This is my pencast about the Lambda Calculus. It's divided into several parts, and you can watch each of the parts separately. Maybe you'll want to read a bit of the text after you've watched the first part of the pencast, or maybe you want to watch all parts and then read the text. That's up to you. But do watch the pencast before you read the text. Anyway, there are 4 parts. The first one is about the syntax and semantics of the Lambda Calculus. And we'll be looking at the pure Lambda Calculus first. And once we've had a look at that, and really there isn't very much to say, we'll say, hey, it's time to extend the pure Lambda Calculus so it becomes more of a programming language, and then we'll look at the applied Lambda Calculus. And once we've done that, in the third part of the pencast, I'll look at type systems for the Lambda Calculus. First, I'll look at the simply typed Lambda Calculus, which is really what happens when you take a type system and use it on the applied Lambda Calculus. At least that's the first attempt. Soon you discover that there's a lot of things. There are lots of things you can't really do in the simply typed Lambda Calculus, so you go for a stronger type system, which is the polymorphic Lambda Calculus. And it also turns out that the polymorphic Lambda Calculus is really the foundation of all the typed functional programming languages that we have, such as Haskell and the ML family of languages. So, to get us started, the first question to ask is, why bother? Why is the Lambda Calculus even interesting? Well, the Lambda Calculus began in the 1930s. At that time, it was a model of computation, and it was devised by, well, Alonzo Church. And here he is. Alonzo Church was an American mathematician and logician. He lived from 1903 all the way up to 1995. So he lived long enough to get his own email address and experience the emergence of the internet. Alonzo Church was active around the same time as Alan Turing, and Church is the Church of the Church-Turing thesis. In fact, what Turing was not aware of when he worked on Turing machines was that at the exact same time, Alonzo Church has this very different but equivalent model of computation, and what Turing does is that he proves that Turing machines and the Lambda Calculus are actually equivalent. And Alan Turing ends up doing his PhD in the United States with Alonzo Church as a supervisor. So originally, the Lambda Calculus is a model of computation, but these days we primarily think of it as the foundation of functional programming languages. In every functional programming language under the sun, there will be a version of the Lambda Calculus. Sometimes there's an awful lot more, but the Lambda Calculus is always buried in a functional programming language, and all the notions of type, all the notions of implementing functional programming language come from notions of typing the Lambda Calculus and of implementing the Lambda Calculus. So in order to understand functional programming, it's important to understand the Lambda Calculus first. And as you shall see next time around, functional programming languages are actually quite neat. And I'm completely unbiased when I say this. Anyway, so the work on the Lambda Calculus began in the 1930s with the first work on the Lambda Calculus as it was, and then later on, in 1940, Alonzo Church came up with the simply typed Lambda Calculus. And then, much later, in 1977, the polymorphic Lambda Calculus was invented, and it's due to Hindley and Milner. in this first part of the pencast, I'll focus on the first work of the Lambda Calculus, because that's what everything that happens later on is based on, and that's the pure Lambda Calculus. First, let's have a look at the syntax. Before I introduce the syntactic constructs, and there are not very many, in fact there are only 3, the important thing to understand is that lambda expressions, because these are the ones that we'll be defining in the syntax, lambda expressions, they're not functions. But they describe what you can do with functions. And what is it that you can do with functions? Well, you can do 2 things with functions. You can define functions, and you can apply functions to arguments. So this is really what you want in a language of computable functions. And later on we shall turn lambda expressions into actual functions when we look at the applied lambda calculus, but for now it's the pure lambda calculus. Here we go. So this is the pure lambda calculus from the 1930s. And let's give it an abstract syntax. What have we got in our abstract syntax? We've got 2 syntactic categories. One is the category of variables, and we'll use X to range over that category. And we'll have a syntactic category of expressions, and we'll use E to range over that syntactic category. And we'll be assuming that there are countably infinitely many variables, so we can always dream up a new variable if need be. But the formation rules for expressions are really quite simple. An expression can be a variable, or it can be an expression of this form. And this is called an abstraction. Think of it as being a function with formal parameter x and body e. And then you have the last construct of the lambda calculus, and that's, maybe I should give this an index, E1, E2, and this is called application. So while abstraction captures the notion of defining a function, application denotes applying a function to its argument, because E would then typically be a function of something that would evolve into a function, and then this would be the argument. So that's really all you have in the lambda calculus. It really is a very tiny language. But now let's go on to see the semantics of the lambda calculus, and that is tiny too. And it's a small step operational semantics. Now in the semantics of the lambda calculus, the transitions are of the form E1 evolves into E2. These are not called transitions, these are called reductions. And in our semantics, well, we speak of reduction rules instead of transition rules. And there's only one reduction rule, in fact, and that's the rule called the beta rule. And what is a beta reduction? A beta reduction tells us what happens if we have an application where one part of the application is an abstraction and the other part of the application is something else. So this rule says that if you have an application of this form, then what you do is you substitute the argument into the body. So this becomes E1, where x is now substituted by E2. So because the lambda calculus is intended to capture the idea that this is a calculus about defining and applying functions, then that's what you need. So this looks simple enough. There's a slight complication in the definition of substitution. and a small example will show you why there's a complication. It's the problem of name clash. And to see why name clash is a problem, consider lambda x, lambda y, x, y, and then let's apply that to y. And given what we know about scopes and free and bound variables, we know that this x is a bound variable and its scope is the body of the abstraction. This y is a bound variable and its scope is the body of its the abstraction that it's bound in. But there's another y here. And that's where the confusion comes in, because this y and that y, they stand for different things. They stand for different entities. The y on the left is a placeholder for what you will receive. This y is the name of some global entity. So if you reduce naively what you will get, if you don't think about this, then you will get lambda y and y. But hey, that's not good, because this is the global y, this is the local y, you can't tell the difference, and both are captured by this. Oops! Name clash. What do we do? The solution? Rename bound variables. So let's try and do that. So lambda x, lambda y, x, y, y is renamed into lambda x, lambda z, where z is some variable name that we've never used before, x, z, y, and now substitution does not cause a name clash, and this becomes lambda z, y, z. Ah! Wow, that's much nicer. So really what we're doing here is we're defining substitution in such a way that we're avoiding name clashes. And here's the definition of substitution. So if we have an application, how do we define application for that? We're replacing x by e2 in this application. Well, we replace x by e2 in e1. Oops, we don't need that bracket. And then in e double prime, we do the same. We replace x by e2. So that was simple enough. How about a variable? That one is slightly more interesting, because this is where the actual substitution happens. And there are two cases. One is the case where y is x. If that's the case, then we get e2. If y is not x, well, y just stays y. There's nothing to substitute. The third case, and that's the one where we need to take name clashes, or the potential for name clashes, into account. If we have an abstraction, lambda y, e prime, and in that we're substituting x by e2. Now there are three cases to consider here. The first one is that y is x, then there's nothing to substitute, so this is just lambda y e prime. In the second case, y is not x, and it's the case that y is not a free variable in E2. In that case, it's simple also. We can substitute into the body without worry. So this is E prime, where x is replaced by E2. But the third case is the one where y is not x and y is a free variable in E2. So here x was not a free variable, but here x is a free variable, so there are y's in E2, and there might be a name clash if we're not careful. Or there will be a name clash. In fact, there will be a name clash, so we have to be careful. So here we write lambda set, where set is a fresh name that we've never used before, and then we replace the bound y by z inside the body, and then within that body where y has been replaced by z, we can substitute x by E2, and there will be no name clashes. And that's the trick of defining substitution. And now that we have defined substitution in such a way that we can define it, now that we have defined substitution in such a way that name clashes will not occur, the beta rule is well defined, because the beta rule relied on this notion of substitution. Yes. So, to round off, let's have a couple of examples of reductions. Here's one, lambda x, lambda y, x, and let's apply this to x, z. Well, this then becomes lambda y, x replaced by xz, so this is xz. Another slightly more interesting example is this one, and this also points to an interesting problem. Lambda x, xx applied to lambda x, xx. Well, let's see what happens. We replace x by lambda x, xx, so this becomes lambda x, xx, lambda x, xx, whoops, and this is lambda x, xx, lambda x, xx, whoops, we can go on forever, can't we? So, these point to two different cases. This one cannot reduce any further. There's no way we can use the beta rule here. This one can reduce forever. This is what we would call a normal form. And here we'll see that this is not a normal form, and in fact, there's no way we can reduce to a normal form if we start with this expression more formally. We'll say that lambda expression E is in normal form if there is no E prime such that E can reduce to E prime. And we'll say that E has a normal form if it's the case that there exists a normal form prime, such that E in some number of steps can reduce to E prime. And a natural question is, if all expressions have a normal form, and the example that we showed here on the previous screen shows that it's not the case that all expressions have a normal form. And we say, because not all expressions have a normal form, this means that the lambda calculus is not what we call strongly normalizing. Of course, one may wonder if there might be strategies that would always result in a strongly normalizing calculus, or if we could do something else that would result in a strongly normalizing calculus. And when we introduce type systems, we will see that the simply typed lambda calculus is a subcalculus which is strongly normalizing. But we'll get round to that eventually.